fabulous students. So this is assignment 7 in chapter 6. And I want to talk about, I definitely want to talk about a bunch of stuff. I want to talk about average value. Yeah, I want to talk about average value today. I notice it says f int there as well, so please make sure you can evaluate integrals with your calculator. I showed that in the last video, I believe. You definitely want to be able to do that. Okay, so today I'd actually like to start with some bell work. And my first question for you is 1. How did we find average velocity last semester? What did we do to find average velocity? Do you remember? I hope so. We did average velocity on A to B is going to be S of B minus S of A over B minus A. And the reason we did that is we're looking at, slope formula here, also known as the rate of change in position with respect to time. Because we're going across an interval, it's the average rate of change in position with respect to time. And that's why we've got average velocity. Velocity is change in position with respect to time. And average velocity is the average rate of change, or the slope of the secant between those 2 points on the graph. This is my graph, and A is over here and B is over here. Then the average rate of change is going to be the slope of that secant line that connects them. Okay, so now I'd like you, with that in mind, I would like you to find the average velocity on 1 to 3 given S of t equals t squared. Okay, why don't you do that now? Well, I like to think it would be done about now. So I want S of 3 minus S of 1 over 3 minus 1. I'll actually say it's really smart to write this on AP if you're doing a free response question, and then show me the answer. So S of 3 is 9, S of 1 is 1 over 3 minus 1. And so I end up with 8 over 2, or 4. You could, of course, on free response stop here. I'm stopping there. The average velocity on S of t from 1 to 3 is 4. Okay? I mean, part of writing the sentences at the end of these problems is for you not just to tell other people what that number represents, but also to remind yourself, maybe more importantly, about what that number represents. That number is the average velocity on this position function from 1 to 3. Okay? And we know that as that average velocity shows itself as the slope of the secant between 2 points, whereas instantaneous velocity would be the slope at a point on position. Okay? Not the slope between 2 points. That's average velocity. Or is it? So today I'd kind of like you to do this. Now I'm finally ready to transition to today's stuff. So remember we just had S of t equals t squared on 1 to 3. Okay. So what I would like you to do is to graph v of t on 1 to 3. Because I want to see if we can answer the question, what is average velocity? But instead of looking at the position graph, I want to look at the velocity graph. So please graph v of t on that interval. All right, well, we know that v is s prime, and so we've got 2t. And I know the line y equals 2t is going to look like that. But I'm only interested on the interval from 1 to 3. So there's 1, there's 3. Excellent. Now, the average velocity is not v of 1 plus v of 3 divided by 2. That's the most common mistake. Students really want to say, hey, average velocity is going to be the average of the velocity here at t equal to 1 and the velocity here at t equal to 3. Yeah, no. I mean, occasionally it works out that way, but remember, a broken clock is correct 2 times a day. So, no, that's not how we find average velocity. Because this presupposes that there's only 2 velocities. There's the one at this moment in time and the one at this moment in time. And sure, if those were the only 2 velocities, I would add them up and divide by 2. But that's not the only velocities. There's the velocity here, and the velocity here, and the velocity here, and the velocity here. How many velocities are there between 1 and 3? And I hope you said that there's an infinite number. And so what I really need to do here is add up the infinite number of heights from 1 to 3, and then divide, not by 2 numbers, but by the infinite number of numbers here, right? So finding average velocity is adding up all the velocities and dividing it by how many you had. Now on the front of it, I'm thinking, damn, there's an infinite number of heights here. And so I'm adding up that infinite number of heights. But then I have to divide that number by how many numbers are there from 1 to 3. And so I'm going to be dividing by infinity. And this is going to be a very awkward sort of situation for us. You know, that's infinity over infinity. That's an indeterminate form right now. So what I'd like to do is think about this situation, okay? I'd like to sort of think about, okay, what if instead of an infinite number of heights, I just had a lot of heights, okay? So what would I write? Well, I know that if, let's say I got, I don't know, n heights between 1 and 3, and I want to add these up. So I'll say, okay, I'm going to take the height at the first x value plus the height at, in fact, I could even use an h. I'm going to use, yeah, let's make it just that general. F of c sub 2 plus f of c sub 3, and so on until we get to f of c sub n. Okay. Now, what's c? Remember from our intermediate value theorem, c represents a specific x value. And this is saying the first of those specific x values, that x value. I plug that x value into our function, and so I get an output, and that's that number. So f of c sub 1 says, what's the height at c sub 1? And then I'm coming over here to the next one, which is, of course, infinitely closer than that, and I'm saying a specific x, in fact, the second specific x, gets plugged into this function to produce this y value, and that's what I'm adding up here. I'm adding up all these y values, and how many? Well, I didn't stop at 10, I went out to n. So we could really have n be infinity, and we've got an infinite number of heights here, but I'm just going to say we went out to the nth term. Okay, we went out to the nth term. So what I'd like to say here is, I could pull out the 1 over n and rewrite this expression this way. I've got 1 over n times f of c sub 1 plus f of c sub 2 plus f of c sub 3, and so on, all the way to f of c sub n. Okay? So I've got that 1 over n out in front, and then I got all that going on. Great. Hey, this is a sum. Remember when we started talking last semester about sigma notation? And sigma was a way that we could, write this sum. And so if I wrote this now with sigma notation, I would say the sum of f of c sub k. I want to add up all the y values based on these specific x's, starting with k equals 1 and going to n. Okay? And is that what I want? Is there a little more? There is. Yes, there will be more. Okay, so this. All right, now what? Well, I kind of actually want to say, remember when we were doing RAM, we said that the subinterval width was b minus a over n, right? So if we were trying to say, hey, I want to go from 10 to 30 with 5 subintervals, how big would that subinterval width be? Well, we would say 30 minus 10 over 5 is 4. We would say then that 4 is our delta x. 4 is our subinterval width. Okay, so I remember this from when we talked about RAM. Subinterval width is b minus a over n. Well, what I'd like to do here is replace this with that stuff. So, I'm sorry, I got n here on the bottom. And so, did I flip that? I have n there on the bottom, 1 over n. Yeah, I think what I want to do is I want to solve this equation for n. So I've got n delta x equals b minus a, or n equals b minus a over delta x. Now here I've got 1 over n. So if this is n, I could take all of this and plug it in there, or I could flip it. And so now I've got delta x b minus a. Okay? And now I'm going to say, okay, this is a constant. It's just that subinterval width. So I'm going to put it over here, because a constant times a function works fine. So now what am I looking at? Well, I'm looking at 1 over b minus a sigma k equals 1 to n of f of c sub k delta x. All right? Now, tell me what this is. What is this? What is that? That's the height, and that's the width. And when we multiply height times width, we get area on the F curve. Area on the F curve. There's my delta x. There's my f of c sub 1. Length times width, I get that area. But remember, we were talking about adding up an infinite number of these heights, an infinite number of these velocities. So this is actually not just a finite value. We want as n heads to infinity. We want an infinite number of these. Okay? So what is this? We actually rewrote these recently when we rewrote our sigmas using Leibniz's really sleek, modern integration symbol. And hopefully what you remember here is this represents this. f of x dx. Actually, we have c sub k in our problem. Here are our bounds, a and b, but don't forget we still have this 1 over b minus a. All right. Well, you know what this formula is? This is the average value formula. So if I want to know the average value of f, that's this function here. If I want to know the average value of that function, if I want to know the average of all those infinite heights, then this is what I do. I add up all those heights. I'm not worried about delta x because if n is heading to infinity, then delta x is heading to 0. So I don't have to worry about that. I can just think about this as adding up all these heights. You're certainly welcome to think about this as a length times a width and that you're adding up all those rectangles as long as you're aware that the width of each rectangle is heading to 0. And so really, in essence, you're just adding up a bunch of line lengths there. Okay, so this integral, but look what we have over here. 1 over b minus a. So this gets me the total of all those numbers, and this divides those numbers by how many? Okay. Does it? No. It just divides by the interval over which I'm doing this. So I've got this nifty new average value formula. If I want to know the average value of, I don't know, f of x equals x squared on 1 to 3, then I know that the average value formula, b minus a times the integral from a to b of x squared dx on 1 to 3. In fact, I can put in my 1 and my 3, my 3, and my 1. So this is going to be 1/2 integral 1 to 3 x squared dx. Well, luckily, we know that if we want to evaluate this definite integral, we want to use our antiderivative. The antiderivative of x squared is going to be x to the third over 3. Remember, if I take this and make it my antiderivative, when I do the derivative of this, I bring down the 3, and I don't see a 3 here. So there must be something present on the original function so that when I take the derivative and bring down that 3, they cancel because I don't have one over here. Okay, so I know that this is my antiderivative, and I feel like putting a plus c, but wait, I only have to worry about plus c in undefinite, Alexa off, in indefinite integrals, i.e. no boundaries. This is a definite integral, it has boundaries, and so I want to take this and evaluate from 1 to 3. Remember though, there's this constant out in front here, and so guess what? That constant is still here. So if I plug a 3 in there, I get 27 over 6, and if I plug a 1 in there, I get 1 over 6. So this is going to be 26 over 6, or if I divide top and bottom by 2, I get 13 over 3. Now, what the hell's 13 over 3? What does it represent? Well, it represents the average value of this function, x squared, on 1 to 3. So here's a graph of f of x. Here's the point 1, 1. Here's the point 3, 9. We're only looking between 1 and 3, and we're adding up all these heights. If we add up that infinite number of heights and divide by the infinite number of heights that there are, we get this. Now let's see if that makes any sense whatsoever. 3 goes into 13 4 times with 1 left over. 4 1/3. We're saying that the average of all the heights from this height of 1 to this height of 9 turns out to be a height of 4 1/3. Sure, I could believe that. That's about 4. I could think that the average of all those heights would be the same. In fact, let's consider this. Let's consider this. MVT for integrals. We remember MVT, mean value theorem. Mean value theorem said if f is continuous on the closed interval and differentiable on the open interval, then there must be some point called x equals c where f prime of c equals f of b minus f of a over b minus a. Right? That was our MVT for functions, the mean value theorem. So we're going to know that the slope of the tangent is the same as the slope of the secant on at least one point from A to B. Okay, that's what mean value theorem told me. Now I'm thinking about a mean value theorem for integrals. And here's what it says. It says, no, that one's good. That's good. It says, if f is continuous on A to B, then there must be some point x equals c. There must be some point, yes, x equals c on A to B where f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. And so what does that mean in our universe? Well, let's think about this for a second. Let's multiply both sides of this equation by b minus a. So I've got f of c, that's the height, times b minus a, that's the width. That's a rectangle. And what should that rectangle equal? It should equal a to b of f of x dx. Now what's this? Well, this is the area under the f curve from a to b. Equals the area of this rectangle? What does that mean? Well, let's take a look at a picture. Let's see if we can have a visual understanding of what's going on here. So I'm saying, okay, I got this curve, and I'm calling it, do I like that curve? No, I want a monotonic curve. Here we go. Okay, I've got a curve, f of x, from A to B. Is f of x continuous on A to B? Sure it is. And remember, the extreme value theorem says if f of x is continuous on A to B, that there must be a min, there must be a max on a closed interval. And yeah, I can see that too. But I'm not talking about this. F of c times b minus a equals, sorry, I'm just so used to writing with those bigger markers. Okay, we said that f of c equals 1 over b minus a, integral a to b, f of x dx. And then we multiplied both sides by b minus a. So we said b minus a times f of c equals the value of the integral from a to b of f of x dx. Well, here's f of x. The integral from a to b looks like this. This is the integral from a to b. It's all this area under the curve from a to b. So what's this? Like, I know over here I'm talking about all that area. But here we're saying b minus a, that's this distance. Right? If this was 7 and this was 4 and I wanted to know what that distance was, I would do 7 minus 4. B minus a is this distance. Well, great, I don't have to do anything with that. Times f of c. There must be some point x equals c such that that y value makes a rectangle with b minus a. And the area of that rectangle would be equal to the area under the curve. So, yeah, I think I didn't place C in a good spot. Let me change that. Because what I want to see is the amount of area here and the amount of area here. The undercounting, the overcounting. That they're exactly the same amount of area and undo each other. So that I can now say, yeah, this height is the function value at C, and this length is b minus a, and so the area of that rectangle becomes that height at x equals c times that width, b minus a. So that area is the same. Now let's walk it back. F of c is 1 over b minus a, integral a to b, f of x dx. Remember how we said this was the average value formula? Well, that's what this is. This represents the average height on a to b under this function. There are an infinite number of heights here. The average height, the average value of all those y values is this formula. Wow. So if we're asked to find the average value of a function, I have to use the average value formula. If I want to know the average value of f equals x squared on 1 to 3, then I'm going to say, great, that's going to be 1 over 3 minus 1 integral x squared from 1 to 3 dx. And then I'm going to say, oh, how do I evaluate this integral? Well, to evaluate that integral, I want to use the antiderivative. The antiderivative of x squared is x to the 3 over 3, and I plug in a 1 and a 3. Great. I'm evaluating the antiderivative to find the value of the integral. So 3 to the third, 27, divided by 3 is going to be 9. And if I plug in a 1, 1 to the third is 1. 1 divided by 3 is 1/3. And so I guess this is 27 thirds minus 1/3. I have 28 thirds times 1/2, which is 14 thirds. All right. So 14 thirds, that's that 4 and 1/3 number again. What I'm saying here is all the heights from a height of 1 to a height of 9, the average of all those heights is going to be this height over here. The average is 14 thirds. Okay? So, average value of the function, I use the average value formula. That's what I've got here. I'm going to use the average value formula. The average value formula is simply 1 over b minus a, integral a to b of that function. Okay? This is the average value of the function. Now, it's terribly, terribly, terribly important that you remember, if I'm looking for average value, not average rate of change, if I'm looking for average value, then I need to use this formula. I need to use 1 over b minus a times the integral from a to b of f of x dx. That's the average value. Okay? Okay, now let's bring up this conversation. Let's say, okay, so let's talk now about average velocity. Last semester, we said average velocity was the slope of the secant on position on the interval from a to b, right? And so we just used slope formula. We said s of b minus s of a over b minus a. Fabulous. There's our average velocity. Notice average velocity involves us using the position function. And that was very confusing for a lot of people last semester. I was looking for average velocity, but you've got me using position. And the reason was because we know that velocity is the average rate of change in position with respect to time, and we know rate of change is slope. So I'm looking for the rate of change I want to know what the slope is. The average rate of change is from B to A on the position function. That, using the position function, gets me the slope between A and B on S, or the average rate of change in position with respect to time, which is also average velocity. But this semester, when we know about integrals, well, now I can say average velocity is the average value of velocity. And so I have an average value formula. I can say the average value is 1 over b minus a integral from a to b of v of t dt. This is also a representation of average velocity, but this representation uses velocity, because what I'm thinking about here is summing up all the velocities from A to B and then dividing. As opposed to this one, which is understanding average velocity as the average rate of change on an interval, not on the velocity function, but on the position function. And it's true that, here comes the next big step, it's true that this average rate of change gets me average velocity, and this average value gets me average velocity. Both of these expressions are equal to average velocity. You need to know both. Not just kind of maybe, but you need to know that this is average velocity, this is the slope of the secant, this is the average rate of change in position with respect to time, and this one, the average value of the given velocity function. There are an infinite number of velocities from A to B, and we are summing them all up. Both of these are average velocity. Okay? This is the average value of the velocity function. This is the average rate of change in position. And that's why I'm using the slope formula. But I want to take this a little step further. And I want to say, look, this is average velocity, and this is average velocity. So, what does that mean I can do with those two things? Well, in my mind, it means I can say that S of B minus S of A over B minus A, that's average velocity using the position function, must equal 1 over B minus A integral A to B of V of t dt. Now, look what happens if we multiply both sides of this equation by B minus A. B minus A. B minus A. Well, those cancel and those cancel. And so now I'm looking at S of B minus S of A equals the integral from A to B of V of t dt. And what's the relationship between these functions? Well, remember, V of t is also known as S prime. And what's the antiderivative of S prime? It's S. And how did we say we would evaluate the integral? We said we would evaluate the integral by finding the antiderivative of this thing and evaluating it from A to B, like that. Ooh. It's kind of powerful magic here. Let's look at this again. I mean, we started with average value. We said the average velocity was equal to the average velocity. We multiplied both sides by B minus A, and we ended up with displacement. Remember, this is just a change of y values on the position function. That's our displacement. And over here, I'm talking about adding up the infinite number of heights under the velocity curve from A to B. Oh. So what I'm getting is, if I integrate velocity, I get displacement. In fact, you already knew that. Remember this, 60 miles per hour for 2 hours? And I said, hey, how far did I go? And we said, well, 2 hours times 60 miles per hour, the hours cancel, and I get 120 miles. And what was that? That's not, I'm now at the rest stop called 120 miles. I'm not in New York now. Instead, it says the change in position from 0 to 2 hours. The change in position from 0 to 2 hours was 120 miles. That 120 miles is my displacement. Wow, there's so much here. Again, you really need to pay attention. Is the question asking you for the average rate of change? I'm doing slope formula. Or is the question asking what's the average value? If we want to know the average value, we have to use the average value formula. If we want to know the average rate of change, we have to do the slope of the secant. Now, what about average velocity? Average velocity can be represented this way or this way. Well, the answer to which one do I need is, what information do you have? If you've been given velocity, use this to find average velocity. If you've been given position, why would you want to take the derivative of position just to do the antiderivative of position? That's crazy. If you've been given position and are asked to find the average velocity, I want to do this like we did last semester. So I have to answer your question, which one should I use, by saying whichever one is appropriate at that time, based on what information you've been given. Okay? So let's look at a function. Here's my function, f of x equals negative 2x plus 4. Okay, there's my function. And I want to consider, let's have this be a function that where f of x is donuts. Gosh, this one's dead too. I'm kind of running out of thick markers, and all I seem to have are these ultra fine points that I'm worried you won't actually be able to see. How about these? Nice. Okay. So let's say that the input x is donuts. I can spell donuts. Donuts. Okay, we've got donuts going in. Do we have donuts going in? No. I want this to be donuts per hour. And I want x to be hours. Do I want that? No, I don't want that. What do I want? No, I'm just going to shut up and say f of x is a donuts per hour function. There we go. And I guess if I plug a number of hours in, yes, x is hours, then I'll get the number of donuts per hour. Fabulous. Okay, so x really is hours for us. Now, what does this mean? 1, 2, 4, f of x dx. What does this mean in the context of this situation? No, I'm not asking you to evaluate this yet. We'll do that, but not yet. And I'm not asking you to tell me what the average value is or the average rate of change. No, not yet. That's coming, but not yet. Instead, I'm merely asking, what does this represent? What happens when I integrate this rate of change? Okay, so think about it. I've got this function here from 1 to 4. So I guess I'm going from 1 to 4, 1, 4, and I'm asking about the integral. Well, we know we're looking at something like that. Okay? So, but what does it represent? Well, I'm taking donuts per hour, and over here we have hours, and when I multiply them to find that area, donuts per hour times hours, I get donuts. So this integral, it represents the total number of donuts. Okay? And maybe it's not the total number of donuts. Maybe it's kind of like the displacement of donuts or the change in the number of donuts. How many donuts did I eat from 1 to 4 hours? Okay, so number of donuts. Okay, great. So if I integrate this rate, I'm going to get this number of things. Now, if I'm integrating and instead of donuts per hour, I have miles per hour, if I'm integrating miles per hour, if I'm integrating that rate, that velocity, I'm going to get position. And so in that situation, if this is miles per hour, when I integrate miles per hour, I'm going to get a number of miles. My change in position, a number of miles different. Okay? So I want to be able to think in terms of these units. I also want to think, hey, if I integrate this rate, I don't get that rate anymore. The hours are going to cancel, and I'm going to get miles. Donuts per hour times hours, those cancel, and I'm left with donuts. Okay, I'm getting the number of those things when I multiply the rate of change times the subinterval width. Okay, but I do want to ask about these other sort of mechanical things. Like, okay, we've got donuts per hour, we've got 1 to 4, we've got this function minus 2x plus 4, and now I want you to ask to answer some more mechanical questions, like 1. What's the average value of f on 1 to 4? And how will we figure that out? Please do that if you can, and come back when you're done. Welcome back. What I hope is that you remember you're looking for the average value of the given function. And because we're looking for average value of the given function, I need to use the average value formula. And so for us, our b value is 4, our a value is 1, integrating from 1 to 4, this f of x minus 2x plus 4 dx. Well, great. I know I've got 1/3 here and here. How do I evaluate a definite integral? I need to use the antiderivative. So I'm going to have 1 over 3. The antiderivative of minus 2x is going to be negative x squared, right? And test it. Take the derivative. Bring down that 2. Now I've got minus 2x to the first. Good. And the antiderivative of that constant is going to be this. So if I take the derivative here, I end up with just the 4 over here. And I want to evaluate this from 1 to 4. 1 to 4. So I got 1/3 times 4 squared is 16, negative 16 plus 4 times 4 is 16, and I get 0. And now if I plug in a 1, I've got negative 1 plus 4, which is negative 1 plus 4, which is positive 3. Okay. Hey, look, I got negative 3 over 3, or negative 1. Now, what does that represent? Well, that represents the average value on our function. No, really, I'm not done yet. I still want to say something about this, okay? Here's what I want to say. Here's our donut function. And we had 2x minus 2x plus 4. So we've got 0, 4, and 1, 2, 1, 2, and we're going out to 4. And if I plug a 4 in there, I've got negative 8 plus 4, which is negative 4. So I'm going to go here, 1, 2, and down here, 4, negative 4. And so there's my curve. Look. See these positive heights? Look. See these negative heights? There's a lot more of these negative heights than there are of these positive heights. My average height, the average value on that function, is going to be when y equals negative 1. There. That would be the specific x value that has that average height, that average y value, from the y value at x equals 1 to the y value at x equals 4. But wait, I'm not done yet. I want to ask, what are the units on this number? What are the units on this number? The average value of the given function. Remember, the given function had hours and had donuts per hour. And so what I see here is the average value in donuts per hour is negative 1. And my guess is you're throwing up a lot of donuts right now. Okay, so there's my average value. My average value is negative 1. I'm simply following the formula 1 over b minus a times the integral from a to b of f of x dx. That's average value. Now, what if instead I said to you, hey, what's the average rate of change? What's the average rate of change in f on 1 to 4? Well, in that case, I'm thinking about f of 4 minus f of 1 over 4 minus 1. And if we're using that same f of x, that minus 2x plus 4, okay, so f of 4 is going to be negative 4 minus f of 1 is going to be positive 2 over 4 minus 1. So negative 6 over 3 or negative 2. Now that's the average rate of change. Does it surprise me? No, not at all. Because we just used the slope formula. And what's the slope of this line? The slope of that line is negative 2. I wasn't expecting to get the same answer. I was expecting to find the slope of the secant on this f function. I used the slope formula and I got this number. This is not the same as the average value, the average y value of f of x on 1 to 4. This is saying, what's the average rate of change? What's the slope across that interval? And of course, because the slope is a constant negative 2, that's going to be our slope on that interval. And what about the units? Well, remember, our units for f were donuts per hour. And on the bottom, we had hours. So this is donuts per hour squared. You know, I know you're fond of saying meters per second squared, and I have no idea what that means. And I certainly don't know what it means when you talk to me about donuts per hour squared. No understanding of what that means at all. However, I do understand the rate at which the donuts are changing. Don't say velocity of donuts. The rate of change in the number of donuts per hour is changing per hour. You know, you could think of, if this were position, I'd certainly be saying, oh look, that's velocity. Oh look, if I divide by another hours, that's going to be acceleration. We don't want to have anyone talking about accelerating donuts here. No, 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 no. Instead, we want to say the rate of change in donuts with respect to time. I'm sorry, rate of change in donuts per hour with respect to time. Okay? Like you were eating 10 donuts per hour in the first hour. And by the third hour, you were down to eating 1 donut per hour. And, you know, we wanted to talk about the average rate of change from 1 to 3 on that donuts per hour function. Okay? So here my units are going to be donuts per hour per hour. I wouldn't mark it wrong if you said donuts per hour squared. I'd just feel uncomfortable. Alexa off. All right, but wait, there's one more question that people confuse. Alexa off. So what I notice is that people are confusing average value with average rate of change. And so we know average rate of change is f of b minus f of a over b minus a. But if we're talking about average value on a to b, on a to b. So if we're talking about the average value, that's when we use our average value formula, a to b of f of x dx. Great. But Mr. Coop, did you show us a little while ago that these things are equal to each other? Not quite. What I said was, if we wanted to talk about average velocity, we could say that average velocity was s of b minus s of a over b minus a. And we also know average velocity is the average value, not of position, but of velocity. So I have 1 over b minus a, and I'm just definitely not enough room over there. So I'm going to go up here and say 1 over b minus a times the integral from a to b of v of t dt. And that's going to be equal to s of b minus s of a. Okay? So yes, these are equal to each other, but only because I'm using two different functions. Average value of the given function gives me the average value of velocity. Average rate of change on position with respect to time is giving me average velocity given the position function. But you have to pay attention. Is the question asking for average value or average rate of change? And by the way, if you're not paying attention to average value versus average rate of change, you'll probably get those wrong. But there's one other that people confuse with these two, and that is total area. Remember, area is always a positive number. And if I'm asking you for the total area, f of x equals negative 2x plus 4 on the interval from 1 to 4. If I'm looking at this situation again, from 1 to 4, what's the total area? Well, we know that if we wanted to find the integral of this, we would say, and we could appeal to the geometry here. And we could say that the height here at 1 is 2, and the height here at 4 is negative 4. And so I know that this height is 2. I know that this distance is 2 minus 1 over 1. So I've got 1/2 2 times 1. Plus, what about over here? Well, this height is negative 4. And this distance, 4 minus 2, is 2. And so I have 1/2 times 2 times negative 4. So what happens? I get 1 minus 4 is negative 3. That's the integral here. I get negative 3 as the integral. I could also find the integral by using the antiderivative. The integral of negative 2x plus 4 from 1 to 4. Okay, let's find that integral. The antiderivative here is going to be negative x squared, right? Because if I take the derivative and bring it down, I get that. Plus the antiderivative here is 4x, and I'm going from 1 to 4. So if I plug a 4 in, I've got negative 16 plus 4 times 4 is 16 minus, what happens when I plug in a 1? I get negative 1 plus 4. So that's going to be 3. That's going to be negative 3. Lo and behold, the value of this integral is negative 3. The value of this integral when I appeal to the geometry is -3. Fabulous. But none of that work answers the question, what's the total area? Both of these are talking about displacement. I added up this positive amount with this negative amount, and I ended up with some number. But area is always positive. And since area is always positive, I have to understand this problem in one of two ways. Either when I appeal to this geometry, I got it positive, that's great, but this one, because area is always positive, no. This one now has to be +4. It's as though I'm integrating the speed graph and flipping that part up. This area, when we were below the axis, what was this area? This area was -4. This was +1. But I want the total area. I want an area of 1 plus an area of 4. And so my total area is 5. Okay? So that's like our geometry. Maybe even our middle school kids could add up those numbers and come up with this value. But now let's think about it calculusly. Notice something important is happening at 2. My function goes from positive y values to negative y values. So what I could do here when I'm looking for total area, what I could do is say, well, let's subtract that negative amount. Right? When we were appealing to the geometry, I'm saying do 1 minus that -4. 1 minus -4 is 1 plus 4, or 5. So there's the total area. I'm taking that positive area and I'm subtracting that negative amount. And that gives me the total area. Or, you're going to hate this next way, but this next way actually shows up a whole lot, so don't be a hater. If I go from 1 to 4 of -2x plus 4 dx, I'm going to just do the integral, which is instead of being the total area, it's going to be the change in area. And I don't want that. What I want is total area. What I want to be able to do is subtract this negative area from this positive area. Okay, so what's that going to be? It's not going to be this. It's going to be the integral from 1 to 2 of -2x plus 4 minus the integral from 2 to 4 of -2x plus 4. Okay? So what am I thinking about here? Well, this is the area under the curve up to the point where the curve hits the x-axis. And this is the area under the curve from the point where we hit the x-axis down to where our function is most negative. When we do this integral, we get a negative number. Total area says areas are positive. So I'm going to get a negative number here, but because of this, negative times negative, I get positive. So I'm going to have this area below the x-axis plus this area above the x-axis to give me total area. Now, some students like, instead of breaking this into 2 integrals, they like saying this. Hey, I'm just going to go from 1 to 4, absolute value, -2x plus 4 dx. And yep, that'll work too. You could definitely do it that way. However, when you then come to me and say, how am I supposed to take the absolute value of this? I'll say, I don't know. I mean, if it's this, I could appeal to the geometry of the situation. But if it's this, nobody, you're on your own. I'm not doing an absolute value of that from 1 to 4. That's crazy. So instead, all the areas that are below the x-axis, I'm going to be subtracting, and all the ones above, I'm going to be adding to make total area. So there are a number of things here that people get confused on. They confuse average rate of change and average value. They confuse the integral with total area. And they confuse all 4 of those things together. And you need to know that each of those things is asking for me to do something different, right? If I'm looking for total area, I want to find the area of all the bits, and the minus ones, no, I'm going to have to make them positive by subtracting those minus ones. If I'm talking about average rate of change, I'm talking about using the slope formula with a function. If I'm talking about finding the average value, then I need to use the average value formula. Okay, do we have anything else? How about a little practice? How are we for time? I'm a little worried that this is already way too long. Yeah, we're at an hour. Okay, I'm going to stop here and notice that there's an in-class worksheet here, average value worksheet. Yeah, I think I want to look at that with you, and so I'll do that worksheet and I'll do some more practice problems in the next video, and that will be for 7 in class. All right, hold on tight because we're not done making these conceptual connections. Not at all. Yeah, 8 and 9. 8 tomorrow, yeah. Definitely bring the bandage to wrap around your head to keep your skull from exploding tomorrow. All right, can't wait to see you. Take care.